I'm Prof Joe. I'm a professor for automation and measurement technology at the University of Applied Sciences in Kempten in the very south of Bavaria. This is part of my lecture series on measurement technology, which is AI Tutored, meaning the AI teaches you all the content and I'm willing to give you some more focus and some more information around that stuff, some more insight by some additional videos explaining not details of the content, but the things around the content, which I think are important. This is chapter 4, and it's just a short recap on electrical engineering and the stuff we need to know for the upcoming chapters 5, 6, 7, 8, 9, 10, 11, and 12, to give you an overview of what you need to know in the area of electrical engineering for understanding the measurement technology we want to make. So, why is it at all important to know about that electrical stuff? Well, as you know, most of the technology nowadays is somewhat based on electrical circuits. So our aim, focus and goal most of the time is to get an electrical value as measurement value at some point at least. Meaning if we want to have a temperature, most of the time we try to get the temperature in form of a resistance, a voltage or a current. We are not aiming to get that voltage in form of a pressure, an air pressure for example. That would make no sense for our way of using measurement values. So I think that is enough to describe the importance of those electrical engineering basics for measurement technology itself, because we want to have just simple electrical signals. Those signals could be digital, and we will talk about digital signals and digitizing signals, but they don't have to be. And at some point, even if in an integrated circuit measuring the temperature, there will be a resistance giving you an analog value of the resistance by an analog value of a voltage, which is internally in the integrated chip converted into a digital value. You readily provided get directly from your chip. But in the end, even those analog currents are still important and are still necessary to get a glimpse of all the measurement values and measurement quantities we want to know. Okay, so what are the important things we need to know? And those are just simple facts you presumably already know. First thing is the simple relation of Ohm's law. R is U over I. Point 1. Then there are the Kirchoff rules, meaning that whenever there's a node with currents flowing in and out of it, the sum over all currents equals to 0. Makes sense. It's like a rivers flowing together. Everything which flows into a point, when two rivers hit, need to flow out of that point in some direction. It has everything which gets somewhere needs to get somewhere else. In the end, it can't vanish at that node. So, it seems to be obvious. Not that obvious is the mesh rule, meaning that whenever we have a mesh in an electrical circuit having some voltages, the sum over all of those voltages in that mesh also equals to 0. Now, how could that be explained? Imagine the voltage is somewhat a force. Now, all the forces in a closed circuit have to cancel each other out. Why do they need to do that? Because when there would be a resulting force within that circuit which is left, that would be added to the next cycle of the circuit, to the next cycle of the circuit. sum up and go to infinity. So that can't be the case. So those voltages have to sum up to 0. Now those are the most important rules we need to know, we need to use. Moreover, resulting out of those facts are some simple rules about a series of resistors, meaning we have a resistor 1, a resistor 2, and we are applying a voltage to them. Now we know the voltage at the resistor 1 is R1 over R1 plus R2 times U, and the voltage at resistor 2 is R2 over R1 plus R2 times U. Yeah, that's, I will call it voltage divider. It's some basic fact which results out of those rules, that a voltage applied to the series of resistors divides in the quantity relation of the resistors on the resistors, meaning the part of R1 over R1 plus R is the part of the voltage which will be at the resistor 1 at that place. That's another important thing we need to know about. Now the last thing I want to talk about is two-pole theory, and we don't need to really know exact details about that. We just need to know why I'm introducing it. So that means you don't really need to be very convenient with two-pole theory, or to be an expert in two-pole theory, or to be able to use it in any which way. You just need to know about the fact that it exists, and perhaps to use it sometimes in simple ways, in very simple ways. But all the exercises we are doing will be solvable without two-pole theory. Most of the time, all of those exercises exert from real measurement techniques. So that means in measurement technology, normally you don't need to do very much two-pole theory, but for our convenience at looking at the things and the measurements, it makes it easier to have some pre-assumptions on what we do have to look at. The idea is the following. Imagine any which complex electrical network. So there can be a lot of voltage sources, a lot of resistors, perhaps even a resistor in that direction over here. That doesn't matter. Now, two-pole theory tells us, okay, let's assume we want to measure the voltage along that resistor. So what we are doing, we do some cut over here, some cut over here. That's point 1, that's point 2. Now we will mark that resistor in green. And now two-pole theory tells us there is an electrical circuit with a voltage and an internal resistance Ri, which indeed has the same behavior as the part over here. So that is accomplished by that. There are rules how to get from here to there. There are some exercises I provide with the content for this lecture. You can train that stuff, but in the end, the important fact is that we get some terminals over here, 1 and 2, which indeed then can be used to calculate the voltage which applies to that resistance. So why do we need that stuff? Okay, summing that up into some simple electrical circuit that's useful. Just looking at it, it's easy to look at that electrical circuit, but it's not easy to understand that electrical circuit. Especially when we know where we want to look at that circuit, we can use the two-pole theory to make a complex electrical circuit to an easy usable electrical circuit. Moreover, now we know that talking about simple electrical circuits, and that's the stuff we will talk about. There are no complex electrical circuits with special elements. No, we only have resistors. Perhaps we will get some capacity or something like that in addition to that, but that's all linear. And so we can just talk about simple electrical circuits. And so since we can assume we have simple electrical circuits, two-pole theory will be applicable to all of those simple electrical circuits we will look at. That means everything we are looking at is reducible to that form over here. We don't have to reduce it to that form, but when doing some thinking about perhaps the influence of the resistance of a measurement device on our measurement, it's enough to look at those simple electrical circuits. By looking at the simple circuits, we include all the complex circuits indirectly. So when understanding the stuff with the simple circuits, we also understand the stuff about the complex circuits, especially in measurement technology, meaning that most of the time this is our measurement device. And that's the important stuff we want to know about. What is the value we get out of there between those two terminals here? For our purpose, it's not interesting what this exactly looks like or does about. It's just interesting for us, how do we get our value over here? And that's the reason why we now can just look at simple circuits for all future chapters and don't have to think and assume complex electrical networks anymore. So, if you like this stuff, feel free and subscribe. And feel free to watch the upcoming chapters about measuring currents and voltages and talking about the systematic errors which occur when measuring those voltages and currents.